we can move over to the next talk by Anton on land use, climate variability, and the Greek polis, new perspectives from interdisciplinary research in Attica and the northeastern Peloponnese.
Thank you very much. Okay, so I'd like to start by thanking the organizers, Andrea and Ruben, for inviting me. It's a pleasure to be here, and the program looks really, really interesting. So I think this will be a lovely couple of days here in Synonymous. The ancient Greek polis, which we may roughly translate as a city-state, though sometimes it was much more of a state, perhaps, than a city, was constituted both by its urban core and surrounding territory. The core provided the fundamental resources for the economic life of the polis, and were in most instances the primary place for food production sustaining the community. Much has previously been written on the content of agricultural production in the ancient Greek world. To a certain extent, agriculture was centered on the so-called Mediterranean triad, consisting of grains, primarily barley and wheat, oil and wine, and which together with pulses formed a substantial part of the Greek diet, even if occasional animal proteins also featured in common consumption. Greek agriculture was generally composed of dry farming, utilizing natural precipitation and stored moisture in the soils. Most of the rain sustained in different forms of cultivation comes between autumn and spring during winter, and interannual precipitation variability was recurrent and seems to have been accounted for by ancient farmers as part of risk management strategies. Agricultural diversification, surplus storage, and trade seems to have been primary measures to counteract interannual variability. Indications of private storage are elusive but nevertheless present in both the archaeological and historical records. Communal large-scale storage and redistribution of comparable to the palace economies of the late Bronze Age does not, however, seem to have featured as part of normal polis strategies. Trade, both through private and public initiatives, played a significant role in providing staple resources such as grain, as suggested already by Garnsey and Morris in their 1989 study on institutionalized responses to supply problems in the Greek polis. Aspects of resource mobilization and exchange are therefore important to consider in regard to the environmental framework of the polis. Periodic lack will have required imports, and in good years, trade networks stretching across the Mediterranean provided channels for selling foodstuffs produced for the market. Access to grain and other staples through regular trade flows suggests that market exchange was an integral part of food security within the ancient Greek polis, despite the projected ideals of autarky in ancient literary texts. Indeed, in cases where grain was offered to individual polis by outside beneficiaries, for example, in the Cyrenian inscriptions, the famous ones from the 328 BC, roughly dated. It seems as though these are offered sort of as part of subsidized prices. They're not actually given to the community. There's no sense of redistribution within the community, but rather things being sold at fair prices within the market. The regularity of exchange and the importance of the market within polis economies can therefore be tied to environmental fragmentation. And this is already shown by Ruben with the corrupting sea. And these ideas tie well together with the framework of connectivity promoted by Peregrine Wood and Nicholas Purcell more than 20 years ago. Importantly, the authors of The Corrupting Sea argued that connectivity and network relationships between central places, such as Greek polis, cannot be separated from their micro-regional or micro-ecological settings. So why focus on trade in a discussion on climate variability? The grain trade and the role of the market in the economic systems of the polis highlight the existence of important buffers aimed at reducing the risk of interannual variability. Bad years would have been manageable if they were interrupted by years with average or above average output, and if other forms of production were sufficient to produce monetary income that would allow grain to be purchased in addition to the consumption of stored grain. In terms of timescales, interannual variability in precipitation can be linked to short-term impact on agricultural production, and in terms of the responses taken by polis communities. Climate change, providing longer trajectories of shifts in temperature and/or precipitation patterns, may, however, have resulted in different forms of insecurities and prompted more profound socioeconomic dynamics. Climate change and societal responses has increasingly become the focus of research on human environment dialectics in both the context of Greece as well as the Mediterranean as a whole, primarily with a focus on prehistory. While some of this research has been deeply focused on climate events and collapses following droughts, other studies have been more nuanced and examine the impact of both increasingly wet and dry periods. Such research has above all highlighted the importance of integrating high-resolution paleoclimatic datasets with human archives in order to examine climate impact in the past. In terms of mainland Greece, the accumulation of new paleoclimatic data from both caves and wetland sediment records has allowed for a more focused and geographically contextual discussion. The proxy data provided by these records can primarily be associated with relative changes in precipitation. 3 Peloponnesian cave records offer sequences that span the early Iron Age and into the Roman period, so covering most of the first millennium BCE. These consist of Mavritripa, I can point there. So Mavritripa cave down here, Alpotripa cave, and Capsia cave here. In terms of the Mavritripa record, there is, however, a growth hiatus between 2952 BP and 2067 BP, so roughly 1000 BCE to 117 BCE. But the Alpotripa and Capsia caves provide complete coverages for these timeframes. These records highlight diverse trends in terms of smaller time slices, but the broader trajectories are largely similar. Above average dry conditions seem to have prevailed in most of the early Iron Age and geometric periods, even if wetter spells also occur within this time frame. In the Archaic period, the signal seems to be more mixed, highlighting shifts between wetter and drier conditions at different times in the Capsia and Alpotripa records. The classical to early Hellenistic period, down to about 200 BCE, is instead characterized by a generally wet climate. In the Capsia record, dry conditions then seem to be present from the late 2nd century BCE and going into the 2nd century CE, while the Alpotripa record suggests a dry spell in the middle of the 1st century CE. The Mavritripa record is difficult to interpret for the late Hellenistic period due to the earlier growth hiatus, but nevertheless seems to suggest drier conditions in the 1st century CE and possibly also earlier. In terms of spatial coverage, correlation maps based on instrumental periods suggest that the speleothems provide a signal that is relevant for most of the southern Greek mainland, including the northeastern Peloponnese and Attica, even if further records would be desirable as they would add to coverage and resolution. Interestingly, a newly published record from the Kocaeli cave in southwestern Turkey indicates a broadly similar picture from that provided by the Capsia record. For the Archaic, the Roman period especially. While it is of course preferable to use local records when comparing climate shifts with land use, the Kocaeli record strengthens the validity of the broader climate trajectories provided by the Peloponnesian speleothems. Paleoclimatic sequences provided by analyses of geochemical proxies in lake sediments instead offer a more heterogeneous picture. These lake records are, however, more sensitive to human impact, as changing land use patterns in the catchment can influence soil erosion and in turn sedimentation, as well as lake water levels. For the current discussion and for this presentation, I will continue to focus solely on the caves for that reason, even though the lake records cannot be completely dismissed. It's currently not possible to translate the relative changes in precipitation and moisture, as seen in the speleothems, into absolute numbers and threshold values linked to agriculture and cultivation. Instead, the trends should be understood as potentially reflecting an increase in the number of years with either above average or below average precipitation. A wetter climate may increase the number of years with high average rainfall, while a dry period may conversely increase the number of years with below average precipitation, which could cause disruptions in agricultural production. If such years occurred more frequently, and especially if autumn, winter, and spring precipitation was reduced, shifts in climate could have a clear effect on the productivity of land use. It is therefore important to take the microregional perspective into account. The Greek mainland is made up of diverse environments at short distances, including a wide range of microclimates, as we discussed earlier. A precipitation gradient is present, with annual rainfall being more abundant in the west, but with annual precipitation dropping off further east towards the Aegean basin. Regions with high annual precipitation would not have been as sensitive to dry conditions as, for example, compared to Attica and the northeastern Peloponnese, where annual average precipitation is around 300 and 400 millimeters respectively. Wheat production requires around 300 millimeters to be productive and around 600 millimeters to produce high yields. Barley is less sensitive and can be productive around 200 millimeters annually, but yields can still be limited with restricted rainfall in the growing season. Olive trees, while to a large extent resilient in dry climates and more sensitive to cold temperatures, can nevertheless be affected by changes in precipitation. The output of olives is generally higher in areas that receive between 400 millimeters and 600 millimeters of rainfall annually, even if cultivation can be successful in areas with lower rainfall. Severe droughts in off years can, however, impact biennial cycle and hinder growth of wood, which can impact yields in the coming years. A dry phase may therefore have had a greater impact in dry areas compared to the wetter parts of the Greek mainland. Given these parameters of climate change, what changes would we expect to see in terms of land use and also in terms of sort of the archaeological record? In the case of increasing precipitation in dry areas, we would expect an increase to boost agricultural surpluses that would allow for an increased consumption and possible population growth. Wetter conditions may also allow expansion of cultivation into new areas of the landscape, as increased precipitation may have facilitated cultivation with thinner soil cover. Conversely, increasingly arid conditions may have created food deficiencies and stimulated contraction of land use in areas particularly with thin soil cover, which would have made possibly previously cultivated fields unsustainable. So how can we then use the archaeological evidence to examine possible changes to climate change? Together with colleagues, I've recently utilized archaeological survey data in order to examine spatial shifts in land use in connection with trajectories provided by the Peloponnesian speleothems. Numerous field surveys in the northeastern Peloponnese provide site data within both intensively and extensively sampled survey areas that can be used to suggest dynamics in land use. But going beyond changes in the number of sites per period, we have examined the extent of possible land use, which we have nicely abbreviated as EPLU, becoming very technical verb. And we used a GIS-based kernel density estimation to produce these heat maps. Kernel density estimation produces heat maps often using a radius or bandwidth for estimation of all input points. For these analyses, we have used a 2.5 kilometer radius to estimate the EPLUs, the extent of possible land use, based on previous models of agricultural catchments. And through these, we have created three-tiered heat maps corresponding to high-density land use, medium extent of land use, and maximum extent of land use per period. Intersection analyses were further performed in the GIS in order to extrapolate the topographic composition of possible land use surfaces in the different periods, particularly related to slope gradients. There are, however, chronological issues at stake when we compare changes in the EPLU with the paleoclimatic record. The climate trajectories are based around high-resolution H-depth models using radiometrically dated samples where measurements are produced between uranium and thorium. The archaeological site data is instead mostly defined through relative ceramic periods, and it's often impossible to determine if rural sites were operating throughout the period. The survey data should therefore be understood as an aggregate of sites per relative period. In order to make comparison with paleoclimatic sequences viable, we have therefore used the Delta 18O proxy from the speleothems to create a relative climate index that follows the archaeological periods and which highlights the number of points in the speleothems falling below the mean value based on the proxy mean for each speleothem record. The adaptation of paleoclimatic records according to archaeological timeframes is therefore a necessary step to produce meaningful comparison. Interestingly, the results from the integrated analysis indicate strong synchronicity between shifts in climate and boom-bust cycles in land use. And you can see some of the results here. I should really stress that these surfaces are the extent of possible land use, and this is the relative climate index, and they are completely sort of different data sets from different data sources. So it's a bit uncanny the way they seem to follow, but there are explanations, and it's probably not as easy as it seems in terms of the correlation of climate and land use. So in the late Bronze Age, we find substantial expansion in a period characterized by humid conditions, while substantial contraction occurs from the LH3C period and into the early Iron Age, when conditions were overwhelmingly dry. In the late geometric to archaic and classical to early Hellenistic timeframe, we instead see an expansion of land use areas that coincide with wetter conditions. In the late Hellenistic to Middle Roman timeframe, land use contraction seems to have occurred under drier conditions. Patterns of expansion and contraction are further emphasized in terms of land abandonment identified in the GIS. The extent of abandonment is substantial in the generally dry early Iron Age, and to a certain extent also in the late Hellenistic to Middle Roman period. Shifts in the spatial configuration of land use are also visible through changes in the topographic composition of the land use surfaces. We have focused on the proportion of sloping land in different periods using Whitelaw's slope classifications to differentiate between land that would not require terracing and land that, so slope class 1, land that would be susceptible to erosion without terracing, slope class 2, and steep land requiring terracing, so slope class 3. In periods characterized by wetter conditions, sloping ground, particularly in terms of the slope class 2, seem to form a high proportion of the EPL use, while in the time frame with above average dry condition, the proportion of high gradient land is usually lower. This can be seen especially in terms of slope class 2, which seems to follow a similar trajectory to the relative climate index. Comparable changes can also be seen in Attica, based on the distribution of farmstead sites collected and here generously provided by Sylvain Attachard. I have carried out KDE analyses in order to define possible EPL use, so extensive possible land use. The trends are clearly similar to those seen in the northeastern Peloponnese. Patterns of land use are fairly stable between the classical and the Hellenistic timeframes, even if a slight contraction of land use occurs. In the drier early Roman timeframe, we can instead observe a reduction in the number of farmsteads and a more substantial contraction of possible land use areas. As in the case of the northeastern Peloponnese, there is also a visible reduction in the proportion of sloping ground in the early Roman EPLU in Attica, suggesting a move away from land with thin soil cover. While the trends drawn from the Peloponnesian datasets can be associated with dynamics linked to the economies of both larger and smaller polis in the Argolid, including Argos, Methana, Haliaeus, and Hermione, the Attic data shows that similar shifts occurred in the territory of an, in many ways, exceptionally large polis such as Athens. The shifts in land use should therefore not only be understood as part of local changes in land use strategies conditioned by the specific polis. But there are, of course, problems of comparability between the Peloponnesian and Attic datasets, since the former is composed of all sites identified through survey and systematically sampled surveyed universes. The point data provided in the form of the Attic farmsteads is instead characterized by specific site types identified through both survey and excavation. The density of farms is further biased by the results of two surveys in southern, and one in southern Attica in the ancient deme of Atene, and in the Masi plain to the north. But even when taking such biases into account, the KDE data is still suggestive of spatial realignment of agricultural production, and such changes seem to occur primarily in the drier early Roman period. Taken at face value, shifts in land use in both Attica and the northeastern Peloponnese thus seems to be impacted by changes in hydroclimate, but a range of other factors need to be considered.
Someone is not muted.
If there's anyone in the audience who's not muted, could you please do so?
So I continue. While climate may have played a part in the visible dynamics, the shifts in land use also coincide with societal changes driven by socio-political events and processes. The shifts occurring between the late Bronze Age and the early Iron Age is an obvious example of major societal transformation by multiple underlying factors. Land use contraction in the late Hellenistic and early Roman period can also be linked with political changes brought on by the subjugation of the southern mainland under Roman control and the subsequent shifts in land ownership structures. A feature of both the late Bronze Age and the classical to early Hellenistic period is, however, the expansion of land use under wetter conditions that may have accelerated land use expansion and pushed population levels. Such expansion may have made production strategies increasingly sensitive to variability and changes towards a drier climate. Increasing agricultural expansion and overuse can create risks even without the factor of climate. As has been argued by John Bincliffe, for example, the intensification of manuring practices in Boeotia during the late classical and early Hellenistic periods may reflect overproduction and soil exhaustion due to increasing population levels. A drier climate added to this scenario may thus further have aggravated vulnerabilities which farmers sought to mitigate through more intensive field management practices. Such sensitivity may also have prompted land ownership changes and the proliferation of larger estates, exploiting land with better soils. Much of my discussion has so far centered on the spatial configuration of land use and how we may connect boom-bust sequences with climate trajectories. But what about cultivation strategies and the content of agricultural production? Ancient texts provide very little information on changes in cultivation over time, and the available volume of archaeobotanical evidence is still limited for the historical periods, unfortunately, even if such data is increasingly being published. Pollen records offer some of the most useful data for diachronic land cover, even if some of the older records are only coarsely dated. The high-resolution record from the coastal marsh of Brauron in eastern Attica provides a particularly useful sequence for land use changes in connection with the fertile Mesogaea hinterland. There are, of course, issues linked with the spatial resolution of the individual signals. The trends seen in terms of grain, cerealia, may be linked to cultivation patterns in the immediate vicinity of Brauron, while the olive pollen, Urea, comes from a broader area within the Mesogaea. The trends for the different taxa nevertheless highlight changes in cultivation strategies, even if at different spatial scales. The record suggests high volumes of olive cultivation in the archaic and classical to early Hellenistic period, but with a slight increase of grain and a decline in olives around 300 BCE and onwards. The reduction in tree crops and the increase in cereal cultivation in the Hellenistic and early Roman period cannot be immediately tied to challenges presented by climate change. The shifts highlighted by the Brauron record may nonetheless be incorporated into a picture of changes in land use and shifts in economic structures. The increase in grain cultivation could signify both concern with the availability of non-local grain through the marketplace, as well as the predictability of the local supply. Syntheses of multiple pollen records from southern and central Greece instead provide a more general trend derived from multiple cores extracted from lowland areas. Using panel regression modeling for the most important anthropogenic taxa, we can produce a more high-resolution, albeit modeled high-resolution picture of changes in agricultural production. The results generally seem to follow the picture provided by the Brauron data. Olives seem to be proportionally more important in the archaic and classical periods, but towards the late 4th century BCE, we can observe an increase in the proportion of cereals. By the early Roman period, the proportion of grain increases further, following a slight dip in the late 2nd century BCE. While olive cultivation does not expand again until late antiquity, the shifts in land cover thus seem to be compatible with spatial shifts in land use observed for both Attica and in the northeastern Peloponnese. The high proportion of sloping ground used in the classical to Hellenistic framework seems partly connected with more diverse cropping strategies. The subsequent contraction and focus on plains and valleys during the late Hellenistic to early Roman period may instead relate to visible increase in the proportion of grain cultivation. So what about climate? By integrating the various datasets, we can discuss the possible effects of climate change in relation to the broader dynamics in land use. The diversification of production strategies in the archaic and classical to early Hellenistic periods indicate that responses to interannual variability were effective. The increase in grain cultivation by the early Hellenistic period may nonetheless reflect increasing population pressure and ecological factors such as soil exhaustion, suggesting a certain degree of stress to the system by the late 4th and early 3rd century BCE. This in part have been prompted by earlier overexpansion, which could have been partly pushed by above average wet conditions in the classical to early Hellenistic time frame. The spatial contraction of land use and the shifts in cultivation patterns in the late Hellenistic and early Roman period suggest more substantial destabilizations of the older systems. Such changes were probably induced by gradual enforcement of Roman rule in Greece, changes in land ownership structures, and the incorporation of Attica and the northeastern Peloponnese into a new Roman economic framework. Increased cultivation of grains, possibly bread wheats, as seen from archaeobotanical studies in the case of Roman Gordium, may not have been a direct response to climate conditions, but may rather have been results of new demand and market structures. Such changes in tandem with a drier climate may, however, have put farmers operating on land with thinner soil cover at a clear disadvantage. Multiple bad years may, in such a scenario, have been detrimental to small family farms producing both for subsistence and for the local market. We are, however, restricted in our interpretations by problems of chronology. More high-resolution data is needed, certainly in regards to the paleo-environmental records, but also in terms of the human archives. A better chronological control of all data categories would allow us to discuss more closely when climate changes occur, as well as the immediate and long-term responses by polis communities in some of the driest and most sensitive regions of the Greek mainland. Thank you.